Here are the sample problems for Class 6 of Math 117. The first one is a very straightforward inclusion-exclusion problem. I've assembled a collection of playing cards, and they have the following properties. The probability of getting a red card is 0.55, of getting a face card is 0.35, and the probability of the union of the two events, that is, getting a card that is either red or a face card, or both, is 0.7. And the challenge is to calculate the probability of drawing a red face card. So this is basically inclusion-exclusion done backwards. You've been given the probability for the union, have to calculate the probability for the intersection. Venn diagrams rarely prove anything, but they're nonetheless useful. So let's draw a Venn diagram representing 4 disjoint events that can happen. So that's face card. That's red card. And our 4 disjoint events are: you get a black face card, or you get a red face card, or you get a red non-face card, or you get a card that is a non-face card and is also black. The trick, as you'll recall, in proving inclusion-exclusion is to write pairs of disjoint events. And in this particular case, if I look at the union of face and red, I can see that that is the disjoint union of 2 sets. The balloon-shaped thing here, F intersect the complement of red with red. In other words, the union is the disjoint union of the circle for red and the part of F that doesn't intersect that circle. And it follows from the axioms for probability that the probability of this event must be the probability of the first of the disjoint events plus the probability for the second one. Then I can write the event F as the union of 2 events. Either I get a black face card, or I get a red face card, and it follows that the probability for event F is the probability of the first of these 2 events plus the probability for the second of them. Now I've set this up so subtracting works very nicely, and I find that the probability of a card that is either red or a face card minus the probability of a face card is equal to the probability of a red card minus the probability of a red face card. Notice I cleverly set this up so that the probability of the event I'm not interested in canceled out. Now we're given numerical values for all of these. This is 0.7, this is 0.35, this is 0.55, 0.55. This is unknown, but it's 7th grade algebra to figure it out. The probability of a red face card is equal to 0.55 minus this, which works out to 0.35. In other words, it's 0.2. And now I can slap these probabilities onto the Venn diagram that I drew. This is the event that's the complement of the union, so this probability is 0.3. We just calculated this probability. It's 0.2. This probability is 0.35. And what's left over, this is 0.15. That's a nice way to check your answer to one of these problems. Well, that was easy enough. Now let me move on to the next one. And let me remember to add a new page and to advance the problem. And the next problem is to prove the inclusion-exclusion rule for 3 events. Again, a Venn diagram is helpful, so I will draw one. And the danger with these Venn diagrams is if you've got lots of events, it's very easy to make the mistake of failing to show that certain events can overlap. In other words, unwittingly in drawing your Venn diagram to imply that the intersection of a pair of events has probability 0. Here I'll draw some nice big overlapping circles for A, for B, and for C. And there, smack in the middle, is A intersect B intersect C. Okay, how do you do this? You use the inclusion-exclusion rule for 2 events multiple times. And by the way, once you've seen how this is done, you would have a very easy time proving by induction the inclusion-exclusion rule for n events. So we need the probability of the union of A union B with C, and we know what that is. That's the probability of A union B plus the probability of C minus the probability of the intersection of those 2 events. Okay, we'll work on the first term in a minute. Just copy it for the moment. And we'll note that the event that either A or B happens and C also happens is the same thing as the probability that A and C both happen or that B and C both happen. And this is something to which we can apply the inclusion-exclusion principle for 2 events. So now I will rewrite the first term using inclusion-exclusion for 2 events. Copy the second term and subtract off the third term. So I have to subtract off the probability of A intersect C, subtract off the probability of B intersect C, and then I get 2 minus signs which make a plus sign, so I add on the probability of A intersect C intersect B intersect C. That means A and C both happen, B and C both happen, Or to put it differently, A, B, and C all happen, and I've got my final result. The probability of triple union of A, B, and C is the sum of the probabilities for the three events separately minus the probability of all the intersections of pairs of events plus the probability of the intersection of the three events. And in fact, this result generalizes in the obvious way. If you have more than three events, you have individual events with a plus sign, pairs of events with a minus sign, triples of events with a plus sign, and so on. Now to finish up, we have a rather fussy real analysis proof, but it's a very, very useful result. We have a continuous function from R to R, and what we want to show is that the preimage of any open interval of the real numbers has to be a Borel set. That means that our Borel sigma field is big enough to deal with the preimage of any possible collection of results, as long as we're dealing with a continuous function. I'll start with the first part by drawing separate diagrams for the domain and the codomain. Here in the codomain, we've got an interval that extends from A to B. It's an open interval, and a certain function value, f of x, is inside it. And now the question is, what is the set in the domain that can lead to values in between A and B? And the remarkable answer is going to be that it is the union of a countable collection of open intervals, hence in the Borel sigma field. So here in the domain, I'm going to show x, and f, of course, takes x into f of x. And then I'm going to consider an interval that extends from x minus 1 over n to x plus 1 over n. A reminder about continuous functions. If f is continuous and you have a sequence in the domain x sub n that converges to x, this implies that the sequence in the codomain f of x sub n converges to f of x. In Math117SP6, I actually use this as the definition of continuous. It's more common to prove that this is equivalent to the standard epsilon delta definition of continuous, and more common yet, I fear, not to mention either of these things in a high school AP course. So unless you've taken a real analysis course before, this may be news to you. That's one reason that this course begins with 1-1 and meets the math department's real analysis concentration requirement. I'm going to prove this by contradiction. So I'm going to assume, I'll even take the trouble to write this down, that I'm making this assumption not because I believe it's true, but because I want to show that it leads to a contradiction, that there is no open interval containing x that belongs to the inverse image. That is, while x itself may get mapped into this interval, no matter how small an open interval I take surrounding x, the function f doesn't map it into some subset of AB. Or, to write it in symbols, no matter how large an n I consider, the open interval from x minus 1 over n up to x plus 1 over n is not a subset of the inverse image of this interval AB. That it always has points in it that lie outside that interval. Okay, if it always has points that lie outside that interval, what I'm going to do for each value of n is I'm going to choose an x sub n in the interval. It's a representative x sub n. It's in the interval such that f of x sub n is not in the interval from a to b. In other words, f takes x sub n outside the interval. Okay, what does that mean? Since f of x sub n is not in a sub b, there is no way that f of x sub n can converge to f of x, because f of x sub n is always outside this interval, never gets close to f of x. This contradicts my assertion that f is continuous, and therefore it can't happen. So here's my conclusion so far. There exists some n with the property that the open interval between x minus 1 over n and x plus 1 over n is in the inverse image of the interval a to b. If I choose n large enough, I get a small interval around x that gets mapped entirely into the interval from a to b. And now, since I want countable sets, I will choose a rational number in that part of the interval, and I will choose a rational number in that part of the interval. So I've chosen a rational p sub x that is an element of the open interval from x minus 1 over n to x, and a rational q sub x that's in between x and x plus 1 over n. Okay, that concludes part A. Now we'll move on to the second bullet point. I need to show that the inverse image is the union of all such intervals. Whenever you are asked to show that two sets are equal, what you do is to show that each is a subset of the other. So let's first start with the pre-image, inverse image, of the open interval from A to B? Well, that is certainly the union over all the individual x's in that interval of the set containing x. That's just saying the inverse image So I just start by saying the inverse image is the union of all the individual points in the inverse image. But we found that each of those points is contained in an open interval that extends from one rational number to another. So that's, if anything, going to be an even bigger set. And that shows that the inverse image is a subset of this union. But we also know that each of these intervals from p sub x to q sub x is in the inverse image, and therefore so is their union. And now that I've proved the inequality both ways, I can assert that these two sets are equal. In other words, for all the uncountable infinities of x over here, I make a little interval that is a subset of the inverse image. I take the union of all of those, and that union is the same as the inverse image itself. Why on earth did we do this? Well, p sub x and q sub x are rational numbers. The rational numbers are countably infinite, and so, as you know, is any pair of rational numbers. In other words, the Cartesian product of the rational numbers with itself is countable, and therefore I can assign a serial number to these, and you may have thought there were going to be uncountably many of them, but there must have been a lot of duplications because we've now concluded there are only finitely many. That lets me do part C. I assign serial numbers to these intervals. In any way that strikes my fancy. And I look at the interval extending from p sub x to q sub x with serial number n. And I call that p sub n, q sub n. With that change in notation, I can now say that the inverse image of the open interval from A to B is the union from n equals 1 to infinity of the open interval from p sub n to q sub n. This open interval is a Borel set. The Borel set, the Borel sigma field, was defined as the smallest sigma field that contains all open intervals from real number A to real number B. This inverse image is a union of infinitely many of these, but it's only a union of countably many, and in a sigma field, a countable union of elements of the sigma field is also in the sigma field, and therefore this union is a Borel set. In other words, the Borel sigma field is large enough to include the inverse image of any open interval in the codomain under any continuous function. I remind you, this only works because f is continuous. Well, that's some rather fussy real analysis, but it's proof that's well worth knowing.